Hi everyone, my name is Jimija, and today I'll be presenting this work titled Database-Driven Multiscale Simulation of Inelastic Materials to an Efficient On-the-Fly Generation of Data. This work has been realized by Dr. Tonghuan Su, Hui Hong, Professor Chen Junshan, and I. This is my outline. I'll go through the introduction, then the methodology of our work. A little bit different than the title suggests. I'll be presenting a surrogate model that we have developed for the multi-scale simulation of composites. Then I'll go through the results and the conclusions. Our main motivation is the multi-scale modeling of composite microstructures. And the ICME frameworks in that context aims to study the PSPP relationships. PSPP, which stands for Process, Structure, Property, Performance. And those relationships include how processes produce material microstructures, how those microstructures in turn give rise to specific material properties, how those material properties affect the performance in engineering scale, and finally, how to select or design materials for a given application. And this is an illustration of the PSPP process. For example, here we might have injection molding as a process for generating a dog-shaped bone specimen. Then this process is going to influence the microstructure of that specimen, where we might have short fibers with different distributions and different orientations. And finally, this microstructure is going to impact the property and performance of that dog bone-shaped specimen when we carry out experiment on it. And to carry out the PSP process in the context of ICME, we rely on multi-scale simulation. And conventionally, multi-scale simulation usually relies on methods such as the finite element methods or fast Fourier transform method. And those methods usually are very expensive in terms of computation time. And because of that, there has been developed many surrogate models that can perform the microscale homogenization of microstructures for us. And this is where we want to do some improvements with regards to how these microscale simulations can be performed. And before introducing our work, I will first introduce the deep material network, which is a surrogate model which has been introduced in 2019 by Liu et al. This surrogate model relies on laminate theory. And its building block is this one shown here. Let's say that we have a two-layer laminate, which also happens to have two phases. We have, let's say, and then let's denote the phase and volume fraction of the phase one by D1 and VF1, and the phase and the compliance matrix and volume fraction of phase two by D2 and 1 minus VF1. Its homogenized properties can be expressed as a function of D1, D2, VF1. And this homogenized function can be derived analytically by applying Einstein boundary condition on this RV. And for generalization, we can add an additional step where we rotate that compliance matrix, which we have obtained here, by some rotation angle theta. Now, let's say that we have a more complicated RV, which we want to represent using DMNs. We can start by initializing an n-layer binary tree. And what we'll do is that we will assign different rotation angles to each node in that binary tree, and we will as well assign activations, which we name Z, to nodes at the bottom layers of that binary tree. And by passing those activations to the ReLU function, we will obtain weights for those nodes. And for the nodes at the upper layers, the weights will simply be the addition of the weights of the children. And given that we have weights for each node, we can also easily compute the relative volume fractions by simply dividing the weights by the weights of the parents. And to perform the homogenization through that binary tree structure, what we will do is that we will assign the compliance metrics of each phase of our RVs to nodes in the bottom of the tree. And then by making use of the analytical solutions which we have introduced in the earlier slide, we can finally express the homogeneous compliance metrics of that RV, but that function H, which is a function of D1, D2, the activations Z in the bottom layers, as well as the rotation angles in the nodes of our binary tree. And the optimal parameters will be determined through training of our network. And previous work have shown that by training the deep material network on linear elastic data, we can then use it to perform the prediction of the nonlinear behavior of the RV for which that DMN was trained for. For example, here we have carried out training for this RV on linear elastic data, and then we can carry out predictions on it, like by using, for example, elastoplastic law, for example. Next, let's summarize the capabilities of the deep material network. Is that after training, the DMN will be able to capture the phase one fraction of its RV. For example, here, let's say that DMN is supposed to represent that RV. By looking at its weights, we can see that after training, that those weights will reflect the volume fraction of each phase in that RV. And as mentioned in the previous slide, DMNs can be used for nonlinear prediction, even though they are only trained on linear data, because they have the physics embedded in them. And some limitations of DMNs is that, let's say, is that they are applicable to only the RV on which they were trained for. For example, let's say that we have two different RVs, then we have to generate two different DMNs for each of them. And we want to improve on that limitation of DMN. And for doing that, we propose this approach where, let's say that we have a RV. What we'll do is that we will mesh them. And then this mesh, we choose to represent this mesh as a graph, for example. And that graph of nodes and edges, we've selected to represent elements in the mesh of our RV as nodes in the graph, and edges between elements in that mesh as edges between nodes in a graph. And then by passing that graph to some function, we can obtain some geometric encoding of our graph, which we then combine with the parameters of DMN. And finally, by combining them, we then obtain a new DMN, which can compute the homogenized properties of our RV. And here, for that aggregation part, we've chosen a simple addition for the angles and multiplication for the weights. And that new formulation for the homogenized properties of our RV, we can write it as a function of D1, D2, a function of our graph, weights and angles in that core DMN. Next, by using such a structure, we hope to be able to handle different RV topologies. Let's say that this DMN is the one that we have been able to train through some data. What we wish to be able to accomplish is that we can use new RVs which we have not seen during training. We can mesh them and then transform them into graphs, and then hopefully by combining the encodings of those new RVs with the DMN that we have trained, we'll be able to derive new DMNs, which will then be able to be used for the prediction of those new, the prediction of the properties of those new RVs. And this slide here summarizes our pipeline. We have our input RVs, we mesh them, transform them into graphs, and then pass those graphs to some graph convolutions, and then some graph pooling. And then we finally pass them to some density, which will then output some geometric encoding. And as introduced earlier, after combining those geometric encodings with our DMN, will then be able to produce new DMNs for the prediction of the properties of our RVs. Now let's see our results. First, we will then introduce our data sampling strategy. For sampling our input data, we've assumed that the compliance metrics of the phases in our RVs are isotropic and elastic. And because of that, our input space is, our sampling space is a simple two-dimensional space determined by the Poisson's ratio and the Young's modulus. And in more detail, we fixed the Young's modulus of the phase one of our RV, and we varied the Young's modulus for the phase two. And for the Poisson's ratio, we've sampled them from a uniform distribution, which is limited by 0 and 0.5. Then for generating the homogenized compliance metrics that we will use to evaluate the prediction of our model, we've performed 3 sets of tests on our RVs. And from those 3 sets of tests, we then be able to construct our homogenized compliance metrics. And to do that, we've used the RV package from LS-DYNA for that purpose. And our input for our training data, we've considered 4 types of RV topologies with volume fractions of approximately 10%, 20%, 30%, and 40%. And for each of them, we've generated 300 samples, and we've split those samples into 80% for training and 20% for validation. And for each of those RVs, we've transformed their meshes into graphs. And these are our training results. We've seen that our model has been able to learn very well how to perform the homogenization of those RVs. And aside from that, it has also been able to learn the volume fractions for each of those RVs. Even though we had 4 different RVs as input, it has been able to learn the volume fraction of each of those RVs. And here we show again the results of the volume fractions, but in more detail. By looking at the numbers here, we can see that the predicted volume fractions given by our model, they are all below 1% in comparison with the target volume fractions of our RVs. Next, in order to see the prediction of volume fractions in more detail, let's introduce the tree map. Let's say that we have this DMN model with those weights in those different nodes. And in order to draw a tree map, we start from the top node here. And its 2 children are those 2 nodes. And the weights are represent respectively 40% and 60% of the weight of the root node. So because of that, we will start from that square here, and we'll divide it into 2 parts here, 40%, and there, 60%. Then we go to the next area here. Now we have those 2 new children with fractions of 20% and 80%. Previously, we've divided in the y direction. Next, we will turn to the x direction. And here we'll have here 20% and 80%. And similarly for that node here, we'll do the same and have 50%, 50%. So that is how we will draw a tree map. Now we can see here, this is the DMN, which we have trained, which we have generated during training. Then after combining the parameters of this DMN with our input RVs, we've been able to generate those new tree maps, which are completely different from the tree map of the initial DMN. And the volume fractions computed from those tree maps, these are very close to our target volume fractions. And these are some additional results to show how those different volume fractions have been changing during training. And here on the left is for the core DMN. And here, those are those interpolated by combining the encoding of each of those RVs with the parameters of this core DMN. Next, we turn to online prediction to see if our hybrid GNN-DMN model can perform the online prediction. The prediction of the nonlinear properties of our RVs. And here we first look at the predictions for this 10% RV, and we see that for both the shear and the uniaxial tests, we see that the predictions are close to those given by a direct numerical simulation. And this is the same for the 20% RV, 30% RV, and 40% RV. Next, we look at the interpolation capabilities of our model. During training, we've only seen 10, 20, and 30, and 40% RVs, but here we look to see if our model can interpolate on RVs with 15 and 35% volume fractions, which it has never seen before. And here we see that by looking at the predicted volume fractions, we can see that they are close to the target volume fractions that we have. And the online prediction as well is very close to. Next, we then see if our graph can extrapolate on RVs outside of its sampling space. And here we see that it extrapolates not very badly on this RV, which has a volume fraction of 44%. But the results are not as good as the interpolation results, but this is understandable because we're working outside of the sampling space. And here we find, and this is the same for the online prediction, which is not as good as the interpolation one results, but this is an understandable result. And finally, for our conclusion, we've seen that multiscale modularization of RVs can be performed by combining the graph representation of RVs with a deep material network. And our hybrid GNN-DMN model is able to capture the topological structure of RVs. And we've also seen that our RV has interpolation capability where it can interpolate on microstructures that it has not seen during training. And finally, we will do further research to see if we can improve on the interpolation capability of the GNN-DMN model by using more complex ways of combining the encoding from the graph convolutions with the parameters of the deep material network. And this is all for my presentation. Thank you.